Yeah, greetings. Might as well start. I know you're all having a good time talking to each other, but let's talk to each other as a bigger group now. Let's see, looking ahead, I was going to announce today the exact day that projects are going to be due, but I don't have the calendar and everything all worked out. I'll just suffice to say that it's a day earlier than you thought it was going to be, so work hard. Probably it'll be about the middle of Dead Week because it takes me average of an hour to read these exams. Well, oh, you know when Dead Week is? Which is? First day of finals is June 6th, and commencement is. Yeah, commencement is a Sunday the 16th. Okay, so that means my grades have to be in by Thursday, before commencement. So I should have a. So let's. Yeah. So I'm thinking right now then that the project should be in by Wednesday the 4th. Is that it? Is it Wednesday the 4th?
Wednesday, the 4th is Wednesday.
Yeah. Okay. So Wednesday, June 4th will be day for projects to be due, and that's an absolute deadline. If they come in on the 5th, I might not be able to read them. So please remember, I announced that at the very beginning of the quarter that they would be due that approximately before finals week, and that there would be no late solutions allowed. So I'm repeating that now, and I'll try to repeat it every day for hereafter, so that you know what to work for. And then now. Next week, starting on Monday, so the 3 lectures next week are going to be special about technical writing, and there will be special handouts for those, and it's something that I've sort of an annual event in this course, which people say they've enjoyed in the past. So I hope you enjoy it this year. If I can still give it with the same enthusiasm I've given it the last time. But this is something that it's sort of different, because you're going to have English lessons in a computer science class, except we're going to be talking about computer science E's instead, and math and how to tricks of the trade for good technical writing. That starts a week from today. Now, what I wanted to talk about today was something about external memory devices, and especially for searching on them. We've talked just a little bit about disks already, and want to review that quickly. I think everyone knows the way that disks, typically the hard disks, work. You've got. Can we have this picture on the screen? You've got these different. You've got these different tracks. What do you call them? Strata, surfaces. What are the platters? Yeah. So those are all accessible at the same time, and then we've got an arm that usually moves in and out, so that you get to that you can get to everything, but it takes you a little while if the arm has to move. Now, on the other hand, there's some disks have one head on every track. The track is this thing. This is a circle, a circular area here, which takes you one revolution time to get around. Sometimes there's one head on every track, or one reading and writing head on every track, so that there's no arm that has to move back and forth, and that's equivalent to a drum storage. And the drum storage essentially says that there's no seek time to move an arm, It's just the latency time latency time is the time to go around to get at the data. That's one version of which sort of is halfway between random access and disk access, because the seek time is cut down. Seek time is the time to move the arm. Latency time, the time for rotational delay to get at the part of the data that you're interested in. Now, to cut seek time down to 0, you either arrange that you're working entirely in one cylinder, namely, different layers but the same arm position, or else you get yourself a head per track or a drum. Now you can also eliminate latency delay completely on a lot of hardware devices. Some of them are designed so that you can't really do this without major hardware modifications. But lots of disks you can use this method as shown on the last. It's shown schematically here on this next page. I'm looking at page 363 of the text right now. If you have a half of a track of data and the thing is whirling around this way, and if say the read head is at A when you want to start reading, well, that's great. There's no latency delay. You just read it, and then half a revolution later, you're done. Now, if the read head is at B at the moment you say begin your read instruction, or write instruction, it's the same for read and write. Then you have to wait a fourth of a revolution for latency delay, and then 1/2 is the read-write time, which you're committed to get that much information. On the other hand, what about the situation C? Well, there's two ways to do it. On some machines, what you have to do, if it's at C when you give the command, you just got to wait 3/4 of a revolution, and then plus 1/2 for the read-write. But it's not. But actually, what you could do is read this part of the data into the last part of your buffer, and then wait your half. Just wait half of a revolution of latency time, not a whole revolution, and then this goes into the first part of your buffer. So if your hardware and software is sufficiently clever, they can work it out so that you would never need more than one revolution for any disk read. I'm not counting seek time. Now, then the book works out that if you're reading a fraction x of a track, the average time of the track your average delay time goes to 1/2 of 1 minus x squared, instead of for half a revolution. If you took the simple-minded thing that says just wait until you get to the beginning of it, then on the average it's going to it's either a whole revolution or nothing, and on the average half a revolution. Half a revolution can be 10 to 15 milliseconds typically. That's a lot of CPU cycles. That's factor of 4 orders of magnitude or something over your ordinary machine instructions. So half a revolution isn't too good if you have to wait for it, unless your application doesn't mind such delays. Now, if you work it out so that you're always taking a full track every time, then there's no latency delay whatsoever by this improved scheme, because wherever you start on the disk, that tells you where to start dumping it in your buffer, and then you get to the end and wrap around to the beginning of your buffer, and you keep up with the disk, and the latency time is cut to 0. Now that has been implemented on lots of different manufacturers' disks, but other disks are sort of designed in a way that's impossible. The hardware already embedded some algorithm before they knew about this trick, and so they couldn't go back to it afterwards. Okay, now what I want to talk today mostly is the searching problem on external memory, because there are these applications where we have huge databases and we don't want to look at too many things on the disk. If possible, we like to just go right to the right thing if we can. Now, with hashing, if you have an application in which you just are doing retrieval by keys, but the ordering of the keys isn't important to you at all. You just so you never need to know what's the next key greater than this one, or anything about the order whatsoever. Then hashing looks like a winning method, because you can compute a hash function and you arrange it so that you can keep a lot of records on each page of the disk, on each track of the disk, and if you work out the mathematics, it turns out that to even get the disk completely full, it's something less than 1.5 disk accesses will be enough to get you to any place on the disk. On the other hand, there's some problems about maintaining this over a period of time with insertions and deletions and things getting out of order, and I don't have a tablet to write on. Let's see. I got a pen. I got some paper, but I don't have one of those tablets. I got paper. This would be good enough. Oh, thanks. Say, now the people on TV don't get to see our camera operator. Look at that. Okay. More. Okay. Now, before we talk about searching, we might just talk about representing ordinary files on a disk. Like your text files or something, and what should you do if for storing a large text file? One approach is you're editing this file, and the stuff is getting bigger and bigger. So we have these fixed things, each one track long, and they probably each have a pointer to which block is next in the file. But now somebody is editing, and all of a sudden he's decided to insert a new paragraph of text in the middle of this one. So what are you going to do? And one thing you can do is what do they call it on the sales system? Rippling. Which means they're just recopying all the, if there's 100 more blocks here, they just move them down. Now they do allow a little bit of excess space in these at the end, because there might have been deletions in there, and you don't always keep everything tightly packed. Okay, and so after you think about this for a while, you come up with the following idea, and it's the kind of thing that's probably been invented dozens of times by people who thought about this for a little while, and they would say, well, we could always guarantee that none of these things are going to be worse than half full. Everything will be at least half full if we're clever about this. What's the idea of cleverness? Well, in other words, suppose let's, for sake of definiteness, let's suppose that this is 512 words in each of these, okay, and but they aren't all full necessarily, and we have also a place for a pointer. Well, if you try to insert more than 512 in there, so you have 513. It doesn't fit, so you can break that into a 256 and a 257, and neither of those is worse than half full, is worse than half empty, and at least half full. And then future insertions will continue. So you'd have to split one of these occasionally and make it into two. But then you wouldn't have to propagate this all the way to the end, which is a slow operation. It takes a lot of disk accessing. Now, on the other hand, what if somebody's doing a deletion? And so it goes from 256 down to 255 or something smaller. Well, again, it's not so bad. You just find the neighbor who has at least half, and between the two of you, you can share. You can divide up your total resources into two parts, unless he's already kind of low, in which case you could combine with him and merge the two blocks and concatenate them into one. Okay, so on a simple linear list, then it's an easy thing to maintain, is so that these things are always at least half full. If you want it to always be at least 2/3 full, you can see how you could work that out. Try to guarantee two. Well, the idea is that when we do an insertion deletion, we still want to have it 2/3 full, provided that was true before the insertion deletion. We don't want to have to change too much of the disk.
Split two blocks into three instead of one into two.
Yeah, that's it. In other words, if something gets full, then you go look at its neighbor, and you combine the two blocks, and then only if both of those are full would you go on to the next one and maybe split in. If both of those are full, then you'd split into those two into three. Yeah. Otherwise, you would suppress it. And I guess there's heuristics that you could learn after playing around with these things as to how much space to leave there. And Andy Yao gave the mathematics of the situation on the average. If you take this collapsing and merging idea, but that was based on the B-tree philosophy, not on this sequential philosophy. I don't know if this sequential one has ever been analyzed. But in the B-tree case, he proved that the average memory usage would be 69.3%. That's the log of 2. Natural log of 2 is 0.693. This is the asymptotic when you have a large block size. 0.693, whatever, is the average fraction of usage if you got random insertions in a B tree. That's what his theorem was. Now, so this works in a one-dimensional case, and the idea was carried over into retrieval applications. And the paper came out in 1972 by Bayer and McCreight, Rudy Bayer and Ed McCreight. Well, Bayer is, I think he's now a professor in Switzerland, and McCreight is one of the main designers of Xerox hardware and software. McCreight was actually, he taught 144B one year also, about this time, 72, 73. But they were both at Boeing research labs in Seattle, and they never told anybody exactly why they called this B trees, their idea. It might have something to do with Boeing, but it might also have something to do with Bayer. And some people say that they tend to be balanced, and they tend to be also bushy. And what was the other one? No, not binary. What? No, but there was another nice, one of those buzzwords. Buzzy? No. I guess no. Balanced is anyway. You heard about RB trees earlier in this course, And RB is, again, it could mean red and black, and it could mean, it could stand for Robbie, who was Bob Sedgwick's son, who was born about that time, and so on. So there was all kinds of questions about these names that are quite important, as you can see.
They tried A trees and that didn't work.
They tried A trees, yeah. You know you've seen this, you know, you've seen this cartoon where the scientist has on his blackboard, you know, this. Okay. Now, anyway, it's gotten to the point, however, where B trees are so important that this article in Computing Surveys claims that it's really the standard, general, most common file organizations in the world today are now some variant of B trees. This is an article that I referred to. It came out in ACM Computing Surveys. We might have this on the screen. ACM Computing Surveys for June '79, and there's this article here by, I don't know how to pronounce his name, Comer, the ubiquitous B tree, and he's made a survey of lots of different software, different manufacturers, and found out that and other database systems, and found out that really has propagated very fast. The idea was simultaneously invented, a very similar idea was simultaneously invented in this FLIRS project here at Stanford, as I found out the first time I talked about B trees in 1971 or 2. One of the guys taking the class had developed this very similar idea in the database project for the library here. Now, it combines this thing about all nodes being half full with another very beautiful idea, and you've seen the idea in connection with these internal searching in connection with these 2-3 trees. But the idea is that they're balanced. Not only are the nodes all of the same, all at least half full, but also there's balance in the sense that every path to the root has the same length. And here's the formal definition: B tree of order M. Every node has at most M sons, but every node except the root and the leaves has at least M over 2 sons, and the root has at least 2 sons, unless it is a leaf. And all leaves appear at the same level. This is the critical thing. This is about carrying no information. We can discuss that. And then a non-leaf node with K sons contains K minus. So the important thing is that all leaves appear on the same level, so that you know that there aren't any parts of the tree that are sort of degenerate, that there's one, the thing is growing very badly to the left and so on. It has to be balanced. That is, all paths from the root to the leaves are the same length. And this concept might seem obvious now, but I remember when I first heard about it, I never had conceived before of trees growing at the top instead of at the bottom. I guess I was just too much a nature boy. I would see how trees grew, and they would spread out they would grow through their leaves and buds and all that. But this is the opposite. These trees, when they get bigger because the root splits. And it was an eye-opening concept, although. In a way, it's very natural in retrospect, it's very natural. And you start out with a small database. You don't need much. You don't need. You just keep it in one area on the disk. But if it's too big for one area on the disk, well, then you've got to have a directory to it. And so you'd have a two-level thing where you have a directory, and then the single areas on the list. But now if it gets even bigger, then you've got to have a directory to, you got to have several directories, and then you got to have a directory to these directories, and so you've gone to, and so it's split into 3 levels, and this is really all that's going on. So it's a natural concept. It's just that I hadn't thought of trees growing that way before, and they put it together with this idea that every node is at least half full, and makes it a nice tight thing. Now, from my personal point of view, I'm facing writing volume 3 in the early 70s, and I definitely want to treat the question of what to do on discs and drums, but I also see every piece of hardware like this is a little bit different, and there's all kinds of real strange things going on in the different devices, and so millions of algorithms based on how to get around specific hardware characteristics. How am I supposed to present something in a book that's going to be of use, hopefully, by the time I finish writing it, so the whole thing is kind of messy, and therefore, when I saw the idea of B trees, which was much cleaner than the various messy algorithms that people had for putting things all on the same track and then on the same cylinder and then reshuffle every Saturday night, you do a complete reorganization of your file, and all these other all these algorithms that really didn't turn me on as far as their beauty was concerned. When I saw B trees, at least it was much more appealing from this standpoint that I could say, well, this is something that I would like to. I would actually wouldn't mind presenting in the book. It's not as dirty as all these other things, and I had to mention the existence of the other ones, but I figured they would die out pretty soon if with luck, and it seems that the world is never going to be completely tidy as a mathematician would like it, but concepts like these B trees anyway. Are pleasant enough to work with that it probably keeps them going, even though some of the dirtier methods might turn out to be more efficient if you measure them just for specific dedicated applications that they were tuned for, some of the dirty methods. Well, B trees then have these general characteristics, and we can see that they maintain them because we already I think you're all familiar with 2-3 trees and some of the other things, and so it's pretty easy to see how you'll keep this characteristics. What is this one? Now the order M, the way it was defined there, usually the order would be I'll turn it this way for you. This is order 7. If the order is odd, it seems to work out best in that general definition. And the case of order 3 then is just the 2-3 trees. The case of order 7 is shown here, and you can have at most 6 keys in a node, so that there's I think 6 keys in a node is that the rule? Because the number of suns has to be at most 7. Yeah. And so this is an example. So you have so I have these things here, and in this particular example, there's no leaves. Now that's just done to make the first presentation of the idea simple, but there's many modifications of the idea, as we'll see. Here's the root has 2 keys in it. Root has at least 1 key always, but might have only 1. If somebody tries to do an insertion of a new thing, and it goes into one of these places that has already 6 keys, then that one would have to split. You'd have 7, and but you don't split it into 3 and 4. You split it into 3 and 3, because you need 1 key to differentiate between the, so you put a 7th key in there, then you take the smallest 3 and make those into a separate leaf, a separate node. And the largest 3, make them into a second node. The middle one goes up into the parent. Now the parent also has 7. in this particular example. So a double splitting has occurred, and so you take the largest three of those, whatever they are. That new one will probably be, it'll have to be between 677 and 773. So it will be the new middle one. This will split into 3, 3, and then another one coming up into the root. If the root got full, then it would split and go, and that's the way the B tree grows one more level. And now this turns out to be, of course, you usually have order much higher than 7, and so it turns out that you get by with only 2 levels almost always. I mean, if your disk tracks are anything reasonable, you usually find out that you hardly ever have to have 3 levels. And it's a nice way to keep the information in order, in alphabetic order. And you can walk through it in alphabetic order if you want to. Now, why would you want to walk through in alphabetic order? So maybe hashing would be good enough. Well, I guess the reason is that a lot of times the index would be there's say 2 attributes, so that you want to combine. I don't know. You want to go through 2 lists of records in increasing order or something like that. That would be one application. I don't know. You can go in. You can use these anyway, both sequentially and for searching for an individual element. I discussed insertion deletion is just the opposite. If you take out a key, well, there's a little trick that involves. Suppose let's go back to this picture. This particular example that I'm showing here is based on an assumption that keys are short, that records are short. So we're keeping our even though I show a key here 233, there's also the data that goes with the key 233 is stored up in that node. Now that's taking up valuable space if it's a lot of data, because we really want to get a high branching factor as we can in the index. So if there's actually a lot of data going on there, then it's much better to take an alternate organization, which we can talk about later. But if under the assumption that the data that goes with the key isn't too much, then we would store it like this, and we'd have the data stored with 233 up there in the root. What if I wanted to delete 233 now? What would I do in order to keep this? In order to keep this structure? No ideas? Oh, come on. You want to move the book a little? Okay. That's what I have to do in order to delete 233. But it's up there in the root anyway. So 233 was the dividing line, you see, between this branch and this branch. 227s, 241s, anything less? Yeah. Okay, Ken?
Looks like you want to go down the tree and find the first element before 233.
Or after, yeah, okay, before, let's say, 227.
227, and delete it from where it is.
Yeah.
And pull it back up and put it where 233 was.
So you put 227 up here, and then and then we have a hole here. Okay? Now we have a hole here, and there's only 2 guys there, but we should always have 3 in a B tree with order 7. So we should always have 3, 4, 5, or 6 in every node. So there's only 2 left there.
So merge it with the one on the left.
So merge it with the one on the left. Now, what does that mean? We got to bring in the 191, which was the discriminator between the 2. I hope you guys can read sideways, because it's good practice. And then you got 7 keys, 149 to 179, and 191, 197 to 11. You got those, and then out of those 7, we would put the middle one up in there, and shuffle them around a little bit. So we'd have to. So this deletion would actually require going down the tree and doing a little combination of these 2 things. Now, before we start talking about strategies where we keep data only we don't keep the data in the middle of the tree, let's just talk about the questions of multiple user access, because that's kind of an interesting thing. Suppose this is a huge database that's connected to lots of different terminals, and it's the entire this database is the census of the United States or something like this, or it's the mailing list for Time magazine or something like that, and they got a lot of clerks answering mail saying, I've just moved, or I'm canceling my subscription because I didn't like what you said about Anderson or whatever it is, and so then you get a dynamic changing database, okay, and you want still a lot of people to be able to access it, and you got to lock out the people. You got to lock things out from, you don't want to update these things twice. You don't want to insert somebody twice or have somebody sending out or charging somebody at the same time somebody else is marking that he's paid his account or something like that. Okay, so how can we handle that? Does the B tree actually is it going to be a big mess? In this way, this is an important problem, and it turned out it was a subject of 3 term papers in this course about 1974 or 5. At which time it was an unsolved problem.
Well, it seems like it might be sufficient to lock the node you're on and everything below it.
Yeah, if suppose you lock the node you're on and everything below it, does that work? Well, the problem with that would be if it depends on how you say which one you're on. Let's go back to suppose the thing was an insertion, for example. See, we saw that if we inserted into this node here, then actually the insertion propagated back and caused this node to split and caused this node to change. Now, if we were going to do an insertion, but it had a chance of coming up and changing this node, then it turns out that we've walked down here, but somebody meanwhile has already made some judgment based on this node. And then if we're changing that node, then we might move this pointer to another one, but he might similarly be trying to split this node and doing something else. So there's a problem of interference that could happen on that. Now the best solution that was that turned out that year on the term papers was due to Baruch, I think her name is, I don't know how to pronounce it. Mohammed, can you tell me what's the proper way to pronounce Baruch? She was from Iran too. I'll write it down. I think it was this. Did I spell it okay? Like that. Okay. Behok. Okay. She had the best solution that year, and was published then in the. It was published in Information Processing Letters. She's now studying computer science in UCLA. See, Information Processing Letters. It's a nice article to look up if you were interested in this problem. October 1976, page 107 to 112. This solution that she came up with was to make sure that all accesses to all work on the B tree goes always from the top to the bottom and never back upwards. Make sure that everything you're going to do is going to go downwards, and you can do this. You can do this by. I guess a similar idea was used in the RB trees. you can do this by just remembering like if you're doing an insertion, you just you know that you'll never have to walk up to a node unless it's full. I mean, it's only in this case where we had a node that had 6 keys in it would we ever have to lock it out. Would we ever have to come up above it? You can actually, for example, you can make sure that there aren't any full nodes. If you come down and see and get to a full node, you could split it right away, and into two half full nodes, and then walk down and release the release the whatever you're working on. It's very important that the root not be locked out very often, because the root is nobody can get at the tree at all unless they have the root. Now there's been some fancy schemes that are circulating lately talking about partial lockout for certain kinds of updates, and you reserve a node instead of locking it, and all kinds of things like that. And that these I guess they're interesting, but I like her solution better, which says you just at all times you just have a lock on two nodes. The one is the parent of the other, and then you move downward, and you have to be careful that you release the locks and pick up the pointers in the right order. I guess what do? You release the father, and then you lock the son or the grandson, and then you move down.
I just have a question about the logistics of the whole thing.
Yeah, Dan?
So two people can be on the tree at the same time.
Yeah.
It's just that the only 2 nodes which you have exclusive access to, or if it's just one node and then its parent.
That's right. So at the beginning, when I'm searching the tree, I would have to wait for the root to be unlocked. Then I would lock the root. Okay. Then nobody can touch that until I decide which way I'm going, and then I choose one of the sons of the root. Okay. Or if the root is already full, I split it at that point. So because every time I see a full node, I'm gonna get rid of it. I'm gonna unfull it. So suppose the son of the root is not full. Okay, then I can go to the appropriate son and unlock the root, and then again pick up from the son's son until I get to the part of the database where I am. So if the database, so typically the things that are locked will be scattered far apart, and they won't be interfering with somebody wanting to update the rest of it. But it's very important that you never want to go upwards from where you are in this kind of application. Okay. So what's the
sort of a natural occurrence when, say, 2 people are separated by on different sub-branches.
Yeah.
That they both fill their respective one above them, and then it causes. So you split a node, and then that causes the one above it to be split.
Oh, but no, the one above it wasn't full.
But if it's happening on 2 separate branches, there's a chance, if that happens, that it does fill up at that point. In other words, there's a separation.
See, you wouldn't ever get to. I'm going to assume that the father is not full whenever I go to a son, and so then if I see the son is full, I would split the son. The father might fill up at that point, but the next person coming through there is going to split it before getting into trouble. That's the approach that I think would work, and similar for empty if you're doing deletions. So this, but the protocols and the locking problems, if you have to go down and up, we had some beautiful solutions to that, but they were 100 pages long, and I'm not sure they worked. I mean, they were.
The top-down approach is going to want it to be a B tree for an even 2-3-4 tree, rather than a 2-3 tree.
Why do you say that?
It's easier to split. That way, you're splitting. When you split the 4 node, you get 2 nodes, both of which are legal, instead of splitting a 3 node and getting a 2 and a 1,
which isn't very good. Yeah. Good point. Okay. Now, then she did simulations in order to validate the method, and it turned out that we couldn't. It was very hard to get parameters where it made too much mattering anyway, because if you assume, for example, that there are how many would there be? 40 clerks processing the timed mailing subscription list simultaneously, and if it takes 50 milliseconds to do each update, or maybe even 500 milliseconds to do each update, still those 40 clerks are typing awfully fast in order to really interfere with each other significantly. So the clashes actually aren't on a steady state situation. The amount of nodes locked out doesn't seem to be a really severe problem when you figure out that if it's people that are causing the if there's some human beings that are actually doing the updating. If these updatings are being generated by machines, then you'd have to be a little more careful about the locking out process. But it turned out that really, even if somebody locked out the whole tree for an update, this wouldn't jam up too badly under most traffic situations that we could think of when she was doing her project. Still, it was an interesting problem to see what would, if you couldn't just have an algorithm where anybody would only be locking out part of the tree. And there's a little bit of it makes some sense also, because you have to be able to take account of errors that have been made during these updates, and keep some kind of accounting about what people did. So maybe you sit and lock out the node for a little while once you get there. Okay. Now, the other thing I wanted to mention is just before we go is what if we want to keep all the information at the bottom of the tree? Well, one of the nice things about this B-tree scheme is that there's no reason why we have to have the same conventions all the way through the tree. We can have different idea at every level, because every level has been formed at a different, at a different time. When the root splits, we can say, oh, we've now grown to a 5-level B tree. Let's keep each level in a different form. And this is typical in any data storage. You would say that you have all your carbon copies of letters that you wrote in the days when you had copies. You keep those in a file folder. But then these file folders are kept in a drawer, and in the drawer you have something in the top. You have a label on the file folder, but then you have another kind of a label on the drawers, and these drawers are maybe shipped out into some archive where they're put into certain certain rows or something like that. So there might be many different kinds of every level in this tree might actually correspond to a different record size, a different physical medium. All kinds of things are possible, but you sort of want to be consistent across any one level. But different levels could be different, and in particular, we could do something quite different at the lowest level that we do than we do at the upper levels. And in the VSAM system that IBM uses, this is essentially B trees with the lower levels with the lower two levels treated specially because they want to be on the same cylinder, and they have pointers going across from you can keep all the data at the bottom, and then in the upper ones just keep numbers that separate the keys, not actual keys themselves. They don't have to really be true keys. They can be any convenient thing that will separate the records, and all the records actually live at the bottom, and there will even be a pointer between blocks, so that at the bottom level we would actually have a scheme just like this one that we talked about for ordinary file. But then we also have an index to get at parts of the file, and algorithms for insertion, deletion, and maintaining of the half-full ratio in the index blocks as well as the others are still similar to what we had before. We don't have to worry about the fact that a key in one of these, though, is real. You have to change this when you're moving, when you're reshuffling adjacent blocks on a deletion, but you don't have to. In many cases, you don't have to worry about the fact that the key that was actually used to discriminate there might not appear in this one anymore until you're doing actually reorganization on a local level. So this is a scheme that has the advantage then of local updating, maintaining a fairly good storage in the worst case. Doesn't require these massive file reorganizations, and also allows a lot of the hierarchical structure also allows things like selective lockout and so on to go on a fairly nice way. That was the advantage of these B trees. Any more questions on that? Yeah?
This structure you're talking about, this being used inside of TSS?
TSS, that's the
IBM time sharing system?
Yeah, that's the one developed in Cambridge. Okay, I'm not sure. I'm not sure which file storage they use here. This is the one that was referred to where KEEA IBM Systems Journal 74. I think TSS is earlier than this.
It's about 8 years earlier than that.
Yeah. Yeah, TSS is a lot earlier. That was Cambridge Scientific Center. That was different. Yeah. Oh, one more point I guess I wanted to make today and I forgot is that the way they implement VSAM is that they know that they use the paging hardware of the machine for virtual memory, and it really would be nice if system programming languages would allow us to talk about the memory pages that are equivalent to disk pages. Then we could write all kinds of software that we could take advantage of the virtual memory in a reasonable way. If you're trying to implement B trees yourself, but the operating system is preventing you from really knowing what goes on the disk, because it's all back. It's by these magic routines that swap in pages out of your virtual address space. All you really want to know is how what size of an array is the right thing for a virtual address space, and couldn't you tell your compiler to get you an array that was lined up correctly in memory, so that so that you could use these techniques. Then you could implement these things very, very cleanly in your Pascal programs and so on. But without that, then you're just taking your chances, and only these system programmers that work at the manufacturers are able to really are able to really make these things work right. So the moral of the story is, on a virtual machine, if you really want to use it right, the programmer ought to have a way to get arrays lined up according to the physical pages, if he wants to, I think. Okay, that's it.